This is the optional help video for the summer assignment in topic 1. This video is definitely going to give you some more detail about using conversion factors that you might not know are conversion factors. So since this is an optional video, you'll have the ability to skip through it as you're watching. I will make sure that I put in the notes at the very beginning, kind of timestamps for when each type of conversion factor is available, and you can skip to what you need, or you can watch the whole thing and add to your learning targets if you feel like it would be helpful. Totally up to you. So here goes. The first thing that I want you to think of, and a lot of you have seen this before, but I want you to know that anytime you have a double unit, in other words, something that is something per something, so miles per hour, or maybe solubility, so much dissolved per 100 grams of water, or density, in other words, grams per volume. All of those are something that we call double units that can act as equalities. So they're situational. In other words, they only work in that scenario that you're talking about right there. It has to be the density of that substance, or it has to be the solubility of that substance at that temperature, etc. But it makes an equality. So for example, 55 miles per hour means that you could say for right then and there, 55 miles equals 1 hour, right? So what I want to do is do a few problems like this so that you can see how they work, and then we'll go on to something different. So in this first one, if I'm going 55 miles per hour, I want to know how long it will take to drive 43.2 miles. I'm going to start with 43.2 miles. And I'm going to set up my dimensional analysis knowing that I need to get rid of miles, and I would like a time unit. And the only thing that I have in my question that will give me a time to distance equation or equality is 55 miles per hour. So I'm going to go ahead and put 50 miles and hours together, and miles per hour would mean in every 1 hour, and I'm going 55 miles per hour, so the 55 goes with the miles, and now I can do the math. They didn't ask me for seconds or minutes or hours or days or whatever, so I'm just going to go with the hours that I know. One thing that we'll talk about in a minute is significant figures, but from my calculator, I get 78.545 and a bunch of numbers. We need to really, at this level, pay attention to what equalities are exact and what equalities are not exact. So if I'm driving 55 miles per hour, the 1 hour is implied as exact, which means it has an unlimited number of significant figures, but the 55 miles is actually not exact. This could be 55.0, 55.2, 49.5, etc. And it's just going to depend on how I recorded it from my speedometer. So this is not exact, which means that it's significant figures, and you have to pay attention to that. Okay? So the exact means unlimited sig figs, and the not exact means sig figs matter. Okay, so in this case, I was given 3. My conversion has 2. I'm going to keep 2 in my answer, which would be 79 hours, because miles cancel. Okay, we'll do another one. Solubility of a salt at a certain temperature of 25 degrees Celsius is 19.6 grams per 100 grams of water. What that means is, in this case, 19.6 grams of that salt equals to 100 grams of water. So I need to make sure that I know which mass I have when I'm writing grams. So I want to know how many grams of water it will take to dissolve 0.253 grams of the salt. So I'm going to start with the 0.253 grams of salt, set up my dimensional analysis. I need to get rid of grams of salt, and I want grams of water, and my equality is the solubility, 19.6 grams of salt per 100 grams of water. So this would be 19.6 to go with the grams of salt, and 100.0 to go with the grams of water. I punch in my calculator, and I see 1.29081, a bunch of numbers, and I'm going to look at significant figures. Since these are both measured values, they matter for our sig figs. Okay, so this would be 3 in my given and 4 and 3 in my conversion factor, so I'm going to keep 3, which would be 1.29 grams of water required to dissolve 19.6 grams of that salt. Somehow I'm feeling, to dissolve 0.253 grams of that salt. I didn't feel like it answer made sense. Always make sure your answer makes sense. Okay, So that ends double units as given as conversion factors, but I do want to talk about a few others that you might not expect. Molarity doesn't sound like a double unit, but molarity is a double unit. Remember that you've learned that molarity is moles of solute per liters of solution. Okay, so it doesn't say molarity, it doesn't say moles per liter, but it is moles per liter, which means it's a double unit. So I can use the molarity as a conversion. Okay, so I'm going to start how many milliliters of solution can be formed from 33.20 grams of potassium nitrate. So I'm going to start with 33.20 grams of KNO3. It's going to be really important to label my stuff so that I know what I'm working with. So I need to get rid of grams of KNO3, and I want to know milliliters of solution. So I need to know this is milliliters of solution. It's not milliliters of KNO3, it's milliliters of the solution containing the KNO3. So I can do this and get myself from grams to not milliliters, but grams to liters. Right? Notice that milliliters are a problem, but I can get from grams to liters, except that I can't because molarity is moles per liter. Okay, so I kind of need to start all over here and walk you through the whole process because I can't do what I wanted to do. So I'm going to come back in and say I need to get to moles so that I can use my molarity. So grams of KNO3 to moles of KNO3. And this is going to come from the periodic table. 1 mole is 101.11 grams. And then from my molarity, I'm going to go from moles of KNO3 to liters of solution. And this is going to be the molarity, which is going to be 0.45 moles in 1 liter. And then I asked you for milliliters, so we have to go from from liters of solution to milliliters of solution. And that would be your metric equality of 1 liter is 1,000 milliliters. And now I can punch my calculator. I got 729.678, a bunch of numbers. Let's talk sig figs. The 33.20 given was 4. The molarity, the grams per mole is kind of up to you what you've read the periodic table for. So in this case, it's not going to limit us. Molarity is a measured value, so it will limit my sig figs, and that means I have 2. That by definition is 1 liter exactly. So the 1 doesn't limit it, but the 0.45 does. And then the metric equality is exact. So this means I have 2 significant figures, which is going to be 730 milliliters. Okay. Let's do another one that's kind of implied like this. This is percent. I love percent because we can get percent in a lot of different ways. We can do percent by mass or we can do percent by volume. But percent, remember, is a double unit. It's a way of saying I have this much of this out of this much total. And it will be a certain amount out of 100 total. So when we do percent, I'll show you how the easiest way to use that is. So a compound is 75.4% by mass hydrogen. How many grams of hydrogen can be obtained from 28.9 grams of the compound? So again, I have to make sure I label everything. Grams of the compound. And I need to get rid of grams of the compound and get grams of hydrogen. And since it's in a compound, it's just H. It's not H2. And now I can say the compound is 75.4% by mass hydrogen. That means for every 75.4 grams of hydrogen, I should have 100 grams of compound. Or I think of it the other way around. For every 100 grams of compound, I should have 75.4 grams of hydrogen. The grams of compound is a definition, so it's exact. Percent means out of 100 exactly. But this would be a measured value. So it's going to be our sig fig limiter maybe. I have 3 in my given and 3 in the percent, so I'm going to keep 3. It came out to 21.7906, but that would make it 21.8 grams of H. And then we can do the same thing by volume. If I'm going to do it by volume, it has to be 100 liters or 100 milliliters total, and then the liters or milliliters, same unit of what I'm looking for. So air is approximately 21% by volume oxygen. How many liters of air are needed? That's the whole solution to provide 3.8 liters of oxygen. So I'm going to start with 3.8 liters of O2. It's O2 because it's oxygen gas and air. I'm going to go liters of O2 to liters of air. The air is the whole here, the part over whole. So the air would be the 100 liters. And it's percent by volume, so I have to do it in volume, right? And then 21% would mean every 100 liters of air have 21 liters of oxygen. And again, now let's look at sig figs. The 100 liters of air is a definition. The 21 would be a measured value, and the 3.8, so we have 2 sig figs. So 0.798 ends up being 0.80 liters of O2. So that concludes using double units as a conversion factor. Okay? All right, let's keep going. Something new for a lot of you is how chemical formulas can contain equalities as well. So we can use the formula to relate the number of atoms to the molecules of the compound. We can use the grams relationship, like almost like a percent by mass kind of grams relationship of the atoms, etc. So I'm going to show you a couple different ways to do this as we're going. So we'll start with just the atoms to the molecules, or the atoms to each other, or the ions to each other in the formula. So the first one is a sample of ammonium nitrate. So the first thing I need to do is write the formula. Ammonium is NH4 1+. Nitrate is NO3 1-, so the formula is NH4NO3. And it has 1.5 times 10 to the 22nd nitrogen atoms. All right, so I want to know now how many oxygen atoms does it contain. So I need to get rid of nitrogen atoms and get oxygen atoms. And from my formula, I can see that in ammonium nitrate, there are 2 nitrogen atoms for every, change colors so you can see it, 3, oh, that's bad, sorry, every 3 oxygen atoms. Okay, so I'm going to go ahead and say 3 O's for every 2 N's, and now I can do the math, which would be 2.25 times 10 to the 22nd. Remember, this is a huge number, and this is atoms of O, and I actually want to talk sig figs. This is a count. We're counting atoms here. These are counting whole atoms. This is not partial atoms, like there is no way for us to do that. This is not a partial number of moles. This is an actual counted number of atoms. So we're going to keep everything we've got. And so our sig figs would be unlimited. We're going to keep everything we're given. Okay? All right, then finally we can do it again. Like, what's the molarity of hydrogen ions in an 18 molar solution of sulfuric acid? So I need to write the formula for sulfuric acid. This would come from the 8 of sulfate, which is SO4, 2-, so I need 2 H's. And I have 18.0 molar, which is really the same as moles of H2SO4 per 1 liter of solution. And that 1 liter is exact, it's a definition. And now from the formula, I want to know the molarity of hydrogen ions, right? And I want the molarity. So the liters are just going to stay, but I need to change my moles of H2SO4 to moles of H+. So there are 2 H pluses in every H2SO4, and I know that from the formula. So 2 moles of H plus for every 1 mole of H2SO4 gives me 36, and this is exact because it's coming from the formula, and the 1 liter is by definition. So my sig figs come from the 18.0, so we'll make it 36.0 moles per liter, or molarity of H+. Okay? We can do this also with math and the formulas, and this is a great twist. It's a great shortcut. I really like this because it saves us a lot of time. So let's look at how this works. we're going to see how many grams of chlorine can be obtained from 25.0 grams of copper 2 chloride dihydrate. So I need to write the formula for that. Copper 2 would be Cu2 plus, and chloride is Cl1 minus, so I need 2 chlorines. And then the dihydrate means, remember that dot is telling you hiding inside those crystals are 2 moles of water for every CuCl2. So the dihydrate tells you 2 moles of water, and they're not really chemically combined, they're physically trapped in there. So we don't put it in parentheses or make it look like a full chemical formula. We just use the dot to say that. So let's start with 25 grams of CuCl2.2H2O and find out, we need to get rid of grams of CuCl2.2H2O and find grams of Cl. So I'm going to use the periodic table as though I'm finding the molar mass. And when I do that, I'm going to find the molar mass of this from the periodic table as 63.55 for the copper and 2 times 35.45 for the chlorine. And then I know water, so I'm going to do 2 times water as 18.02. And that gives me 170.49 grams of the whole thing. And this was the Cl, right? So I'm going to put 2 times 35.45 grams of the Cl. And from the relationship of the molar masses in those compound and the atoms and the elements of the compound, I can find that relationship. So this is 10.3965, a bunch of numbers. This is random conversions from the periodic table, so my sig figs are going to come from my given. It has 3, that would be 10.4 grams of Cl. This is a great twist. We use it all the time. You may want to practice that a lot. Okay, now we're going to shift to squared and cubic to cubic conversions. And this, some of you have done and some of you have not, so I definitely want to make sure that we give you a chance to learn this. But this is where we're talking about a conversion from a volume in cubic length to another volume in cubic length, or a conversion of an area. We don't do area much in chemistry, but an area in squared length to an area in squared length. You're converting squared to squared or cubed to cubed. And so as a rule, you can use the normal equality, but you have to square or cube both the numbers and the units. So let's just do an example so you can kind of see what happens here. I want the area in cubic centimeters, this is what I'm looking for, of sheet metal that's 54 inches squared. So I need to convert inches to centimeters. But I need them to be squared. So I could do this twice, and you'll remember seeing this at the beginning of when we started to do this in Chem Honors if you had it with me. And you can say twice, inches, 1 inch is 2.54 centimeters, and 1 inch is 2.54 centimeters. And then that cancels the inches squared, because you have 2 of them, and you end up with centimeters squared. All right, so I can do it that way, and I can write it out that way if I want to, and kind of go from there. But I'll show you a shorter way also. So this would be 348.38, a bunch of numbers. My conversion, this is actually an exact conversion. So that's unusual. It has unlimited sig figs in metric to English. That's unusual. This is the only one. But my given has 2, so I'm going to make that 2. So that would be 350 square centimeters. Okay. I'm going to show you a faster way to do this so that you don't have to write out all those conversion factors over and over. So we'll do one now. What's the volume in cubic decimeters of a swimming pool that's 6,000 cubic meters? So 6,000 with a decimal, that's 4 sig figs, meters cubed. I'm going to go meters cubed to decimeters cubed. And if I were doing this in linear fashion, 1 meter would be 10 decimeters. But since I've cubed the meters, I have to cube the number, and I've cubed the decimeters, I have to cube the number. So this is really 10 cubed over 1 cubed. All right. If you want, you can figure out what 10 cubed is. I just punch in 6,000 times 10 raised to the third. So when I do that, I get 6 and 6 zeros. okay, which my calculator put in scientific notation, but I need to have 4 sig figs, right? So that means that I need these, because these are exact. Metric conversions are always exact. So they're unlimited sig figs. So I need 4 sig figs. So I can do 6 with 6 zeros if I want, and put a zero over the, or a line over the last zero that's significant, and call it, sorry, that was really messy. Call it decimeters cubed. Or I can put 6.000 times 10 to the 6th decimeters cubed. And both of those would be acceptable to College Board. They tend to like scientific notation better than the line, but they would accept both. All right, so that's squared to squared and cubed to cubed. The last one that I have for you is what happens if it's a volume that's cubed to a volume that's not cubed, like cubic meters to milliliters. There's no such thing as a cubic milliliter or a cubic liter. A liter is already a volume unit. The same thing happens with area like acres versus square feet. Okay, so you definitely want to be thinking of what's happening. So I've given you a couple of equalities here so that we can do this with some English to metric, but you would never have to know them. The only English to metric you have to have memorized would be 1 inch is 2.54 centimeters. So let's see. How many acres is the surface area of an index card that's 15 inches squared? So I'm going to do 15 inches squared. And I see here that an acre is 43,560 square feet. So I'm going to do inches squared to feet squared, because I need to get to square feet, and then feet squared to acres. And notice that acres is not squared. It's already an area unit. Okay, so inches squared to feet squared, 1 foot is 12 inches, but the numbers are, or the units are squared, so I have to square the numbers. And then 1 acre, 43,560 feet squared. This is exact because it's a definition, but this is not exact. So the 1 acre part is exact, but the 43,560 is not. So I have 2 sig figs in my given, and then 4 in my conversion. So that gives me 2 when I'm done. My calculator spit out 2.391 times 10 to the negative 6th. I'm going to keep 2 sig figs, so that's 2.4 times 10 to the negative 6 acres, which makes a lot of sense because an index card is nowhere near the size of an acre. And then finally, we'll do one more with cubic to non-cubic volume. 0.50 gallons of milk, a half a gallon, would be how many milliliters? So I gave you gallons to cubic decimeters and cubic centimeters to milliliters. So we're going to do gallons to cubic decimeters. Remember, a cubic decimeter is a liter, but I want you to do this the long way. Then cubic decimeters to cubic centimeters. And then finally, cubic centimeters to milliliters. All right, so this is easy. 1 milliliter is 1 cubic centimeter. I gave you 1 gallon is 3.785 cubic decimeters. And then if you don't know centimeters to decimeters, you have to go to meters first. But I know that 1 decimeter is 10 centimeters. So when I cube them, I have to cube both numbers. And now I can punch this in, and I get 1892.5, which I'm going to go with 2 significant figures from my given, because the 1 gallon is exact, but the cubic decimeters is not. And my English to metric, or my metric to metric are exact. So that's going to give me 1,900 milliliters. I can show you another way. Let's do it quick so that you can see. We can go gallons, 1 gallon to the same, 3.785 cubic decimeters. And then if you know that a cubic decimeter is equal to a liter, you can do that there. And then you can do liters to milliliters here, which would be 1 liter and 1,000 milliliters, and we're going to get the same answer. Okay, so you can do that either way. So hopefully this was helpful. You'll get some practice in your summer assignment with these. Hopefully this helps you. Let me know if you have questions.